Hello, good evening. Thanks a lot. Welcome to the Bay Area PySpark meetup. My name is Jules Damji, and I'm the Spark community evangelist and developer advocate at Databricks. Delighted to see so many of you here, and I see a lot of familiar faces. So it's actually great to have those people come in week after week and month after month to attend this particular meetups. It's a community like you that actually gets the Spark growing. It is really good to hear people from different assets and different vertical industries talk about Apache Spark and how they're actually using it. Now, we try to have these meetups on a monthly basis. We speak at in San Francisco, we host it in the Bay Area and in the Peninsula in Palo Alto as well. So if you want to speak at the Spark meetup, please get hold of me towards the end. If you want to sponsor and host us, do that. I've got a couple of announcements before we actually get started. Our next Bay Area Spark meetup is going to be in San Francisco at Bloomberg. So if you're a member of this Bay Area PySpark meetup, that's why you're here. You should be able to get a notification in about a week or so. And then we're actually also having our Spark Summit. We held the Spark Summit every twice a year, one in USA and another in Europe. This time we're actually having one in Dublin, not Dublin nearby Pleasant, but Dublin in Ireland. So if you really want to travel up north and across the Atlantic, please come and visit us. How many of you have been to a Spark Summit before? Lovely. It's a great avenue to have all these community actually get together. Now, before we actually acknowledge our host, I really want to thank HP and Aruba Network to really put this event together. In particular, I want to call out to Shirley Wu and her team who actually did an incredible job. So give her a big hand. And Aruba as well, but thanks a lot for hosting us. And before we have, she introduce our first speaker, I'll have Shirley talk about what they do over here and introduce John. Thank you.
Hello, everybody. Welcome. It's a great pleasure to host the Bay Area Apache Spark meetup. First we would like to thank, our marketing, engineering management from Prasad, their support. And of course, the group of people from IT facility and the food services, and also our volunteers to make this happen. Tonight, I'm going to introduce my colleague, John Conley. He started as a theoretical physicist, then moved to the network security, and about 3 years ago, he joined the Niara, which is a early stage startup, developed the user behavior analytics solution for security. So John, me, and a group of other people like Jishen and Martin and a group of other people, we started building the Niara analytics platforms. And so he will present some of the features we developed during that 3 years journey. So that could become from a lot of the late night discussions, chat, and the prototypes. That's what we have accomplished before. But going forward, we'll continue to improve our platform and looking at the new technologies. And for example, Spark on Yarn is our primary computation engine for all the analytics use cases. Going forward, we're going to need more, team members to join our team. And so we are hiring, and we have one slide to show our job openings and descriptions, or just talking to one of us, people to talk about what we're working on, and is that related to what is that interesting to you? And welcome to join us. So here's the job description. So we're hiring now. I'm hand over to John, so he will start our presentation tonight.
Okay, is that working? Okay, I'm going to start a timer on my phone so I don't go over. Let me get my slides. Okay, so yeah, as Shirley said, my name is John Conley. And as she said, I came from a background in theoretical physics, and then a brief stop at Cisco where I started doing network security, and then to Niara, and now here at Aruba and HP. Just a little bit of a plug for Spark in case any of you are here because you haven't tried it and you've heard how cool it is. For someone like me coming from a, non-computer science background, within a few years to be able to build, distributed systems, correlating data at scale, all that's, only made possible because systems like Spark exist, which hide so much of the complexity from you. So, if you are thinking about, ways to scale up your problem or do distributed computing, Spark is a really powerful platform. So, give it a try. So, I'm going to talk about one very practical example of building a solution to a problem using Spark, and I'll talk about how we did it and some lessons learned. So first, just one slide about the product. Originally, it was called Niara, and since being brought into the HP and Aruba family, we're renaming it as Introspect. And it's pretty simple to explain in one slide what the idea is. It's a network security product, and we want to ingest all kinds of data, whatever we think is useful for security. Yeah. This isn't working well? Okay. Is this better? Okay. So the idea of this product, this solution is to ingest all the relevant data and then to make it visible in an actionable way to a security analyst and to automatically create certain kinds of security intelligence on top of it. So, a little picture of what this might result in is, a view of this entity, this guy, Sam Fuller, who, as you can see, is obviously up to no good. So, all sorts of log data, packets, flows, whatever, come in, and we need to make sense out of that so we can tell you that this guy is someone to look out for. So that's the essential gist of the problem we're trying to solve in Introspect. And I'm going to talk about just one very narrow aspect of that problem, which is correlation of the data. So we have different data streams coming in. For example, some of them are network packets or flows saying, what bytes went where on the network. And others are, let's say, logs from various systems. For example, from Active Directory or DHCP, giving us mappings between MAC addresses and IP addresses, or IP addresses and usernames. And we want to stitch all that together so you as an analyst don't have to. And we want to attach to that flow or that packet or whatever the username that tells you who did that. So that's the idea of data correlation. And that's the aspect of the problem that I'm going to talk about today. So here's a very specific example. Let's say you have some packet or flow that has a MAC address and a timestamp on it. It's got other data attributes on it too, but these are the ones that are concern us for correlation. Then you also get some log from DHCP telling you that let's say at 11:15 a.m., we got a lease that is associated a certain IP address with a certain MAC address. And let's say later you get a log from your Active Directory controller saying, at 12:30 we got some login event telling us that a certain user was logged onto that IP address. So the idea is to progressively go through and stitch these things together and then attach, I don't know. Here we go. Okay. Okay, that's better. To go through and attach this extra information, the source IP and the username to this flow. So then it sounds like here's another example, slightly different. If we have some flow going from the DNS server with a DNS request, we might want to know which source IP, whose laptop actually initiated that DNS request. So this, the flow coming from the DNS server doesn't tell us that, but a DNS log that we get as a separate stream of events will tell us who actually requested it. So, using the proximity of the timestamps from the log and the flow, we can stitch together those things and attach the source IP to that flow. So these are 2 examples of the types of correlations that we want to do. So a little bit of terminology about the problem. The data that's coming in, I'm going to call, each data entry I'm going to call a record. And these mappings between, let's say, IPs and usernames, or MAC addresses and IPs, these sorts of things that we use to attach, that we use to enrich the records, I'm going to call bindings, just to give a name to it. So some types of records we enrich by these bindings. Some type of records we extract bindings from, and some serve double duty where we do both. But this process of enriching the records by bindings I'll call correlation. So some complications when we try to do this. A big one is out of order and late arriving data. So if you had all your data, all the bindings, all the records present at the same time in one process, you can imagine this would be pretty easy to do. You could write a quick bit of code to do the lookups and stitch together the data. But if you know that data is coming out of order, like the bindings that you need to do the enrichment might come after the records. That complicates things, because then you've got to think about how you buffer things, how you keep things around and load the right data at the right time. There's also a huge range of timescales here. So certain bindings last a lot longer than others. So if you think about that DNS correlation, those bindings are very short. Essentially you get a DNS log and a flow that refer to essentially the same event in time. So they should be essentially the same time, maybe a few seconds apart. Whereas something like a DHCP lease or a Windows login might last for hours. So we're talking about a huge range of timescales. And if you combine this with high data volumes, so if you have a high volume of, let's say, flow data coming in, or you have a high volume of, let's say, Active Directory logs coming in, then you can imagine that combine that with this range of timescales makes it hard, because you can't buffer all the data in memory or something. It's too much to hold onto. So then you have to think about how to synchronize this data in a scalable way. So a couple more bits of terminology to describe the different kind of temporal models in terms of synchronizing these data streams. I'll refer to one model as current, which is basically the DNS log case, where these bindings don't last very long, and you can essentially correlate one window of records with the same window of bindings, more or less. So you get 10 minutes of records, the same 10 minutes worth of bindings, you can just match them together in that window. In the other case where these bindings can last very long, to give this a name, I'm going to call it keep alive, just because it means, you might get a DHCP lease at 6 in the morning, and you need to keep that alive the whole day, keep it available to do correlation later in the day. So in this case, if you take a window of records and you want to do correlation, that window of bindings can be much, much bigger. And then, of course, there are some cases where, the bindings are timeless. They last forever, essentially. One example, more or less, is, for example, GeoIP. I mean, it's not quite true. GeoIP, the mappings between IP addresses and locations do change sometimes, but for, all intents and purposes, they're pretty much static. Okay, so now that we've kind of framed the problem and defined some terms, I'll talk about the implementation of our solution. And, to sort of prepare you for how we decided to do it, I need to give you some assumptions that we're working with. At the time that we came up with a solution, we were kind of already locked into using PySpark on Yarn for our ETL process, our extract, transform, and load process, where we did this data correlation. So we had a big code base in Python that was already using PySpark. So this was sort of the framework we decided to continue in. And we were kind of locked on the RDD API as opposed to, for example, data frame or Spark streaming APIs, because again, we had a lot of code and logic already based around that. And partially because we wanted to be able to package our application as something that could run on an externally managed Hadoop cluster where we didn't really have control over what was happening on the worker nodes. We could pretty much rely only on Spark or HDFS as a way to distribute data out to the workers. So these are some assumptions that kind of guided and limited how we could go about solving this problem. So the first solution that we tried, and a solution that we actually used in the product for quite a while, it was the first implementation in the product, was to use Redis to do this correlation. So I don't know how many of you are familiar with Redis, but it's an in-memory database. You run it as a server. It's got a single-threaded master that accepts all writes, but you can replicate out to slaves to read-only slaves to distribute your read load. So it's a simple model. If you can run a Redis server somewhere, and if it can keep up with the load, you can just put your bindings in a Redis database, and then when you're running correlation, you can have all your workers for every single record just look up in the Redis database, hey, what is there a binding for this IP or for this MAC address? So it's a very simple model, it's easy to implement, and it works pretty well up to a point. And the basic design, again, was on the driver node where we launched the Spark job, there's a Redis master. And then where we have control over it, we replicate the master with slaves on the worker nodes so that the worker processes in Spark can do local reads against those slaves and to reduce the load on the Redis master and to eliminate the network latency so the reads can be local. We use the Redis sorted set data set so we can do temporal lookups. So you can efficiently say, give me the most recent record before 11 o'clock or something like that. So the Redis sorted set lets you do that easily. To mitigate the network latency issue as constantly sending requests to the Redis server, you can also pipeline requests. So you can take a batch of records, you can accumulate all the lookups you want to do, you can send them in one big batch to Redis. It'll send you back the sort of sequence of responses. So that's something we also took advantage of. Now, since Redis is an in-memory database, you can't just keep accumulating bindings into it. At some point, you have to purge the old ones so you don't run out of memory. So we implemented a periodic purge of old data so we didn't run out of memory. And Redis has a nice feature where you can write Lewis scripts that'll run on the server side, and those are good for doing atomic updates, and they were helpful for doing this purge efficiently. Now, the issues with this, again, we only had a single master running on the driver node. So at some point, we had to write all the bindings into the Redis database. And so you can imagine, at some scale, your master, which has a single thread listening for these writes is not gonna keep up. So we actually, ran into that at certain customers when scale was high enough that the master couldn't keep up with the write load. Now, if we had very late arriving data or very out of order data, we had to try to keep a hold of the bindings in memory long enough to process that data. But if the data load is high enough, you'd eventually run out of memory in Redis when that happens. So, at some point we just had to cut off and say we're dropping the rest of these bindings. And if we get out of order data, too bad, we're not going to be able to correlate it anymore. And the master slave setup that I talked about, where you can get local reads on the worker nodes, that's only possible if you have control over your worker nodes. And at some customers, we didn't have control over the worker nodes. We were an application on the Hadoop cluster, so we couldn't do that. And then during the purge or during times of heavy write, you would actually get read timeouts on the master. And then another complication with Redis is, Redis is a simple database in terms of what you put into it is just streams of bytes. So you had to be really careful about managing your own serialization of the data you wanted to put in. One way we considered helping out, at least with the scale issue of Redis, was clustering. And there, Redis has its own clustering implementation. There are third-party ones, such as the twin proxy one from Twitter. But this has its own complications. Then you have to manually decide how you're going to shard your keys. There's limited support for any type of queries that will cross over into multiple shards. There's no or limited support for Lua scripting, depending on the solution. There was one solution we looked into called Redis Labs Enterprise Cluster, which looks like it solves all this for you. It almost looks too good to be true, but it's it's a enterprise thing that you have to pay for. I'm not sure how much, but and even if that had actually solved these problems, you still need to maintain this separate Redis cluster, which is only possible in certain deployments, and you still have to keep do the purge because it's still an in-memory database. So we decided to move away from Redis. The second solution we tried is to do basically a join. So you've got two streams of data. One is the records, one is the bindings. There are basically some keys you want to do lookups on. So, if you had both these things in a relational database, you'd say, oh, okay, we'll do a join between these based on that key. Now, as I said before, we're pretty much locked into, we're using PySpark and we're using RDDs. So that would be an RDD join. And, we could see how to implement it. You could join the RDDs based on these lookup keys. Then you'd have, a set of records and a set of bindings that share the same key. Then you could loop over these to do this temporal logic to decide which things to correlate with each other. So we looked into this. There's a few issues here that we ran into. One thing is if you look at the actual implementation of the PySpark join, you can look at the source code. Join.py is pretty short. It's based on a group by key, which shuffles all the data for a given key to the same worker. So you can imagine if there's, let's say, an IP or a MAC address in your data that has a lot more records than all the other ones, you get a hotspotting problem where one worker gets tons of data and others don't get as much. So this can lead to, depending on your implementation, this can either lead to a slow processing or out-of-memory issues with one of your tasks. Another issue is that, as I showed on the example slide, we have chains of correlations to do. So we want to do a DHCP correlation to get IP addresses. Then we want to do Active Directory correlation to get usernames. And these are only examples. There's actually, dozens of different correlations that we've implemented. So if you imagine chaining these, they all have different join keys. So you set up this chain of joins, and you end up having to shuffle data based on different keys all over the cluster. So that leads to, again, processing issues with both out of memory or just with things running slowly. Now, those of you who are familiar with Spark might know that data frames support a join operation as well, which you can either express in data frame APIs or in the SQL Spark SQL API. And you might also know that there's this thing called the Catalyst Optimizer that's getting better and better with each release. So it's natural to consider doing a data frame join here. I will say that if you think about how to express that join in SQL or in data frame APIs, it's not trivial actually, given the temporal logic, but it's something worth thinking about. And as I said before, we kind of were locked into using RDDs, so we didn't really consider that as an option. So moving on to the next solution we thought of, we thought, okay, the problem with Redis is bottlenecking on the master and possibly getting out of memory. But what if we basically take that data that we were trying to keep in Redis and write it to disk on the distributed file system so that memory is not an issue? Then the only question is, how do we get it back to the workers when the workers need it to do correlation? So this is the next approach we tried and the one we ended up sticking with. So we write the bindings all to HDFS. When it's time to do correlation, we read the relevant part of those bindings into each worker's memory, and then we do the joins local to the worker just by doing lookups in Python data structures. And again, for those of you who are familiar with, for example, data frame joins or whatever, this is very similar to a broadcast join, where the left-hand side of the join gets distributed across the cluster, and then each worker can do the join locally then. Now you could imagine splitting by the join key so that each worker doesn't have to load all the data, but then you have to partition your records by that join key, and that involves a lot of shuffling, especially since there are different keys for each stage of the correlation. So we didn't do that. We just have each worker load all of the relevant data for that time range when it's time to do correlation. Okay, so the pieces involved in putting together this solution. One is you need to extract the bindings from the incoming data. And this is all configuration driven. So you just configure what fields need to go into that bindings table. And to get into the implementation details, we have basically a sequence of transformers that run. I have a DAG here. It's because depending on what's in the record, you may run some transformers and not others. So there's actually a graph of transformers to run. And then somewhere you get to a place where you say, okay, this is the right kind of record. I'm going to extract a binding from this. And we create a PySpark row object. So then we've got a bunch of rows. As many of you probably know, that makes a data frame. And we take that data frame and we write it to HDFS using the Parquet file format. And one good thing about Parquet is that it enables high degree of compression. So these files are pretty small. So we can store a lot of this bindings data on HDFS without using a ton of disk space. We also enabled an optional pluggable pre-aggregation logic. So for example, we could do things like deduplication in this data frame before we write to Parquet. So to deal with this long-lived binding issue, for example, these long-lived DHCP leases, we did a type of long-term aggregation. So when we process the bindings in the first place, we process them in small time buckets, like 10 minutes worth of data at a time. And then to prepare the data for correlation, we would do an aggregation step where, depending on the temporal model, we would bring records from one bucket to the next. So this is especially important in the keep alive type where you have long-lived bindings. So let's say, in the 11 o'clock to 11:10 bucket, we have a DHCP lease that maps an IP to a MAC address, and that's going to last for 8 hours. Then as we go on in time, we keep that one, we push that one to the next bucket, 11:10 to 11:20, then to the next, then to the next. So that when it's time to do correlation, we don't have to go back and load all of the data from the beginning of time. We know we've already aggregated the relevant data to the current time. And you only need to worry about the most recent binding for each key. So if that gets superseded by a new binding, we can drop that one and only keep the next one. So now we've talked about how we get this bindings data to HDFS. The next question is, how do we load it into the workers when it's time to do correlation? Now, those of you who are familiar with Spark might think, oh, we need to get some data to all the workers. Let's use a broadcast variable. And that is what we tried first. So when it's time to do correlation, you load the appropriate buckets of bindings data from HDFS, you get a data frame, you collect it into a Python data structure, and then you broadcast it using the PySpark broadcast variable. there is a problem with this, which is that, at least in PySpark, at least in the version we were using, the broadcast variable distribution is very expensive. Well, first of all, you need to collect the data to the driver, which can take a while. Then you need to serialize that data using Pickle. Then you distribute it to the workers using a torrent protocol, and then the workers need to unpickle it. So just that serialization and deserialization and the collect part can all take a while. So to get around this, we did a very sort of brute force thing of just dumping the data straight to HDFS. So again, when it's time to do correlation, we load the data frame from Parquet, we load the relevant bindings into a data frame, and then we serialize each binding. To get into details, we use MessagePack just because it's an efficient serialization and fast. And then we dump these serialized records straight to HDFS using save as text file. So there's no collect step. We're using a faster serialization than Pickle. And that was a big enough speed up that this would actually work. And then when it's time for the workers to read that data back from HDFS, they actually use a Python HDFS client called Snakebite to read it straight from HDFS. So here's how the correlation lifecycle looks. You have your records that you want to enrich. You read them into an RDD. You run a map partitions on that RDD, and in each partition, you do this you use a Snakebite client to read all this correlation, the bindings data, into the memory of that worker. And then you can just loop over the records. You extract the keys you need to look up the bindings. Then you loop over correlators, and you look up the relevant bindings. And first you need to use a key to look up, and so that's a dictionary lookup. And then you need to find the right timestamp, for example, the most recent one before a certain time. And for that, I simply use just the Python bisect library to do a binary lookup in a sorted list. And then you update your lookup keys. So for example, you do your DHCP correlation to get a new source IP. The source IP in turn gets used to look up the username in the Active Directory correlation. And then when you're all done, you have all this data you extracted from the bindings, and there's some logic for updating the record with all that data. So we try to make this as configurable as possible to make it easy for developers to add new correlations without having to write too much code. So in addition to the temporal models we already talked about, we put in some configuration knobs. One is called delay tolerance, which is basically, if we're going to correlate, let's say, these flow records with, let's say, DHCP, how long do we want to wait around for the DHCP? What if the DHCP comes 10 minutes after the flows? What if it comes an hour after? At what point do we say, oh, we're just going to give up and go ahead and process the flows and not do this correlation? For those of you who have worked with streaming frameworks, that's close to the notion of watermarks that they use, for example, in Spark streaming. We also have a notion of left and right boundaries. For example, for DHCP, you might choose something like 8 hours to say, I'm not going to consider DHCP leases longer than 8 hours. So that would be your left-hand boundary of 8 hours. You don't look for DHCP bindings more than 8 hours before your flow. And in some cases, you might get more than one binding in that time range. So another knob is, do you want to take just one or two or whatever? And then there's some knobs for the update logic. For example, if you don't find a binding, what do? Do you just leave that field off, or do you have some default value you apply? And another piece of configuration is do you force the update? For example, if something else put an IP address in your record before the correlation got there, do you overwrite it or not? So here's an example of the configuration for this DHCP correlation we talked about. So the temporal model is the keep alive, because DHCP has long-lived leases. These left-right boundaries are 8 hours on the left and 0 on the right, because we can consider bindings up to 8 hours before the flow, but we'd never want to consider a binding after the flow. and you only want to take the most recent one, so that's limit equals 1. And if we might say if something else, if some other mechanism like like an agent on your laptop or something, put an IP address there, we might not want to overwrite it with whatever DHCP is telling us. It looks a little different for DNS correlation. The temporal model is current because we're only looking for close by bindings. So we might only care about bindings within a minute on either side. And we might only take one from either side. One configuration we might want is, if there's a log that comes just before the record or just after, and one that comes just after, do we prefer one over the other? So that's the preferred side equals left. In addition to the configuration, we put in tons of places where we could put in pluggable logic, because we wanted to make it possible for developers, you can't imagine everything that developers are going to want to do and make everything configuration driven. So we tried to make the logic in various places pluggable. So for example, how you pull the bindings out of records, there's an extractor that you can override with your own Python code if you want. If you want to do some deduplication before writing the bindings to disks, there's an aggregator you can plug in, and so on and so forth. So one thing we found when actually using this framework in the field was that it was pretty hard to debug, because this is a PySpark job running on a cluster. If something goes wrong and you say, hey, why didn't that record get correlated with that field, it's pretty hard to go back and figure out exactly what went wrong in the code. So one thing we added was a debugger. So given a batch of data that was run through this correlation and some kind of filter, for example, a single record ID, you run this thing with those options and it'll rerun the entire correlation in a local mode. So instead of running in Spark, it'll pull all the data from HDFS and then run actually in a local Python process, and it'll drop into the IPDB debugger at various points and let you just inspect what's going on. So we found this, both in development and in customer support to be pretty useful. Okay, so that's the overview of what we did, and just to talk about the status with it. This is a correlation framework that's in our product, and it's been working. It's been alive and well in our product for a couple years now. And since its inception, we've managed to add a bunch more data sources and a bunch more types of correlation. So it's been pretty extensible. And it's supported the stability and scalability we've needed so far. But in terms of what we need to improve, we still need better latency and throughput on this thing. And although we've extended it a lot, as we scale to more customers, it needs to be easier to extend. So these are the things we're thinking about now. So some lessons learned from this whole process. Data correlation is a messy problem, especially at scale, and especially when you have delayed or out of order data. There are no sort of easy out-of-the-box solutions for that. You have to make some trade-offs. Spark and PySpark it's an exceptionally powerful and flexible platform. But you do have to sweat the details, meaning you can easily get yourself into trouble with, tasks running out of memory, things like that. And so you do have to understand a bit about what's going on inside it to know why things are working well or not. And some sort of more high-level things I feel we've learned from this effort. You're always going to run into trade-offs. You don't want to go too far either way. So, in terms of a quick implementation versus optimal design, I would put what we've done here on the side of quick implementation. It worked. It took advantage of the power of PySpark. A more optimal design might have used more of the high-level APIs, might have used Spark Streaming or the data frame API, for example. So, you could spend, and a similar trade-off is, do you build it yourself, do you build all the logic yourself, or do you try to use the features of, state-of-the-art frameworks? And again, I would have put this effort on a little farther and build it yourself. you could spend your whole life trying to keep up with the advances in all the various frameworks, so you don't want to go too far that way either. But you should be aware of what's out there and take advantage of the power of what's out there. Okay, thank you. That's all I have today, and I welcome any more ideas from you.
Well, thanks a lot, John, for sharing this interesting use case. Now, we only have one mic, so I'm not going to run around. I'll have you come up here and ask any questions that you have so I can go back to him. I've already done my 10,000 steps on the Fitbit, so I'm not going to run around. So do we have any questions for John? Yeah.
Hi, so my problem may not have the same latency requirements that you do, but did you consider using a graph database for this kind of work?
Did you consider a graph database?
Yeah, I mean, we considered everything, and definitely a graph database. At our previous job, we actually looked a little more deeply into certain graph databases. For example, the now defunct Titan. But yeah, I think a graph database in its conception will solve this for you, because all these correlations are just taken care of by establishing new edges, and then to discover the kind of correlations we want, you just have to do a graph traversal or whatever. So it's a totally different way of thinking about the problem. I don't know enough about sort of the performance and stability and everything of the existing graph databases to know if it would have scaled and all that, but I mean, it's certainly a worthy thing to try out. Yeah.
Why don't you choose Redis instead of Memcache? Memcache is a lot faster. That could cut down on your latency.
Why didn't you use Memcache?
Yeah, I mean, I don't know. I honestly don't remember the time. What our, Memcache never came into our thinking. When we said, okay, let's try an in-memory cache, we just went straight for Redis. It worked really well. Latency with Redis was not a problem. The latency was fine. It was the load on the server at high rate, and it was the bottleneck in the master. So whether Memcache would have solved that, I'm not sure. It's possible. But yeah, it's a good question, but we never investigated Memcache, to be honest.
Any other questions? All of you are quite front.
So did you use Redis cluster or single Redis? Did you use Redis cluster?
We did not use Redis cluster. So as I mentioned on the slide, we use master-slave replication. We did not use clustering of the master. And for a while, it worked fine for us. When we started running into issues, we did consider that, as I had a slide about Redis clustering. So we considered it. So there's a few caveats for Redis clustering. The main one being that in most of the clustering solutions, you have to come up with a partitioning of your key space. And many of the operations that you want to do on Redis, including some of the things that we were doing, like with Lua scripts, you can only do on a single partition. So you have to make sure that that operation only touches keys that exist in that partition, in that shard. So we looked at how we were using Redis, and we realized that it wouldn't translate directly to be able to use one of the sharded Redis clustering solutions. So we decided not to go that route. Now, it's possible we could have changed all our application logic to support the sharding of the key space. That's one thing. Second thing is that there is something called Redis Labs Enterprise Cluster. It might have a different name now. It's like RE, or I forget. But that they claim to pretty much support all Redis operations out of the box. I don't know how it's actually implemented. It's not open source, it's an enterprise thing. So it's conceivable that that could have solved our problem, but there were, there were other reasons why we didn't want to try to deploy some enterprise Redis cluster on top of all the other stuff that we had in our system. And at some customers, it probably wouldn't have been possible. So we didn't go that route either. But yeah, I mean, Redis clustering, both the built-in Redis cluster, the third-party things like TWEM proxy, and this Redis Labs enterprise cluster, they're all really interesting options. But yeah, we didn't go that route.
We're going to take one last question.
You mentioned you used Parquet because you liked the compression. Is that right? Would you get better, but you also emphasized that you need performance. Did you ever look at using no compression with Parquet? Would you get better performance that way?
So the read and write, well, I should say one other benefit of Parquet is the really close interoperability with data frames. So once you write it, when you read it back, you get back your schema and everything. So that's another nice thing. But the read and write time was negligible compared to everything else. So that was not a bottleneck. So enabling compression to reduce disk space was worth it because the time it added for uncompressing at read time didn't matter compared to other bottlenecks in our.
John, are you going to be around after the meetup to answer more questions? Sure. Okay, John is going to be around, so if you have any more questions, please get hold of him. So give a big hand to John from Aruba Networks. Thank you.